Good afternoon and welcome back to this final session in our bite-sized corrosion winter series, where we will be tying up our discussion about the ECDA process. I think that we've really had a really valuable discussion through these past couple of sessions as we've looked at ECDA, or External Corrosion Direct Assessment, the process which is described in the NACE SP0502. Now, as we've discussed over the past few sessions, the process of ECDA is really divided into four main stages. Now, in that first stage, that's the pre-assessment stage, we take note of the physical characteristics of our pipeline, its physical environment, and its operating history. And that leads one almost naturally into the second stage of indirect assessment, where one gathers data from multiple field surveys. And then using those findings, we would select locations to directly assess the pipeline surface in the third stage. And then the key bit is putting it all together, entering into that post-assessment stage where we can evaluate the process, compare the pre-assessment and indirect inspection predictions with the actual findings from our direct inspection. We can try and determine the root causes of the corrosion, obviously implement suitable mitigation measures. And finally, we can provide a comprehensive integrity rating with respect to external corrosion. Now, today it's great to be able to welcome Neil Webb back to the microphone, and we're going to discuss some practical aspects of actually implementing ECDA and looking at some of the findings. So welcome, Neil. The ECDA process is actually quite comprehensive, but also fairly complex. Would you agree?
Yes, for sure. The process is very rigorous, and that is necessary when you are using this process to actually justify the continued operation of the pipeline in terms of legislative requirements or an operating license or something like that. But it's not necessary to always use the process exactly according to the standard. That standard is there so that you can say to the regulator or the inspector, well, I have followed this process and therefore I have done what I need to, and my pipeline is functional and it's safe to continue operation. But we frequently use the same concepts in integrity management, where it is not necessarily a regulatory situation.
I can understand from a regulatory perspective, at least if there is an incident, one can say, well, we did due diligence, we have proof. But the ECDA standard practice developed by NACE was only developed in the early 2000s. But it really wasn't a brand new concept at all, as far as I can tell.
Well, no, the actual procedures that we go through have been in use for much longer than that, but not necessarily rigorously applied or documented in such a formal manner.
Yeah, and I know you've seen just a few projects in your time in the industry.
Yeah, one or two.
Just a few, yeah. Shall we look at some applications of ECDA and how it was applied, perhaps not as formal ECDA, but where it was useful and how its findings could be implemented?
Yeah, well, here's a really good example of a pipeline project which actually exhibits all the characteristics of the ECDA process, even though they did not take place in the formal step-by-step method and timing that is envisaged in the 0502. So this particular pipeline, fairly long pipeline, had been in disuse for many, many years, and it needed to be reinstated. And the question was, what is necessary to be done to allow this pipeline to start functioning again? It was known that the pipeline was leaking. It was known that the cathodic protection system was not in full operating condition. We had a full resistivity survey of the entire route. We had the topography. I mean, you can see in this photograph the pipeline route stretching out for literally hundreds of kilometers. And there are many, many different environments along that route, both from a topography point of view and from an environmental condition point of view. Now, this photograph is actually taken during some of the rehabilitation work, but it shows you the absolutely horrendous ground conditions, literally putting the pipeline in through a swamp,
Yes.
where the ground is extremely aggressive. And so in this project, we then did a current demand survey. We had the resistivity data. We had potential data, pipeline potential data, because there were test posts every 2 kilometers. We knew which cathodic protection systems had been working and which had not been working. And we obviously had the topography as well. And we knew where the leaks were. So we had a huge amount of information that is all part of the pre-assessment phase. And from that, we were able to then designate some fairly extensive zones in terms of the ECDA terminology, where we needed to firstly replace the pipe where it had obviously leaked. And this is actually the old pipeline. It was perforated. As you can see, it resembled a piccolo. And those sections were then replaced with a new factory coated pipe. Then there were sections of the line where the pipe itself was in good condition, even though the wrapping had failed. And these sections were line wrapped. There you can see an overline wrapping machine with the holiday detection rolling spring running along behind it. There were sections where there were isolated areas of wrapping damage with not much in the way of corrosion. You can see here the excavation of the areas.
That's a brave TLB.
That TLB operator was incredible. He could guide that bucket to within millimeters, and he never once hit the pipe. It was amazing. Wow. And in this photograph, you can also see over there, that guy over there is actually doing some butter welding to weld up a fairly significant pit, an isolated instance. And these sections were then rewrapped for obvious reasons. There's that wrapping's not doing much good anymore, and the new wrapping was applied by hand. So
there was quite extensive repair work undertaken, but did that fix all of the problems, or did you do further studies? Having replaced the sections, rewrapped, reinstated cathodic protection and so on, we then carried out a further potential survey, and we came across a situation where there was a particular test post, if you have a look here, where there was one particular test post that the potential was low compared to the ones on each side. And as a result of that, we requested the contractor to do some excavations along the length of the pipe in between these test posts to try and get a better idea of what was going on. It was actually a good illustration of the effect of timing, because we had asked for these excavations to be done. I had then disappeared down the pipeline to the other end to go and check something whilst they were busy digging. And the project had got to the point where they were pressure testing the pipe. And I came back from my excursion and went to inspect the holes, and we discovered the pipeline had found the defect all by itself. So I very excitedly went through to the project office to talk about what had happened, and walked in on this very gloomy group of people gathered around a table, glaring at each other and not really feeling very communicative. And I discovered that they were all down in the dumps because the pipeline had just failed its pressure test. So I said to them, well, gentlemen, I can tell you where the leak is. Well, you could have heard a pin drop. After that, they kind of took corrosion and corrosion protection a little bit more seriously. They were quite astounded. The point about that was that the ground conditions in that area were pretty bad, and the cathodic protection had not functioned. So in this slide, you can also then see that had we done the full pre-assessment situation, we would have picked up from a close interval survey that there was a significant area of poor protection from a corrosion protection point of view, and probably would have done something about it. This was actually done before the implementation of close interval survey. And this project was one of the first really big implementations of close interval surveying in the early 80s. There's a concern in my mind that sometimes when you get data like that, your 2 points on either side, 2 test posts on either side are fine, and one that's not so good in the middle. is there's a tendency to write off that as being a spurious data point. And I think this shows that if you do get unexpected data, in this case, poor protection, it is worth investigating a little bit more. It might not be spurious and to be ignored. It may in fact highlight a problem, such as you identified here.
Yes, for sure. I mean, you can see that this level of protection falls off almost instantaneously from a distance point of view. In the ideal world, if the pipeline was uniformly protected and the wrapping was in uniform condition and was sitting in uniform soil, you can say that the test post reading is representative. But if you don't know that, then the test post reading represents 3 meters of pipe adjacent to the test post. And you can see that you just go here and 3 meters away, there is no protection at all. It is possible.
It's definitely sobering, isn't it? Now, I think we've actually discussed this in a little bit of detail in one of our previous series. And I think we mentioned that all of this information actually prevented them from physically replacing about 10 kilometers of pipe.
Yes, that's right. We spoke about it in the non-intrusive survey section. And what had happened on this same project was that the pipeline started at the coast and traversed about 100 kilometers of very low-lying area, but the first 10 kilometers of it was a swamp. And there was a desire, let's put it that way, to replace the first 10, 15 odd kilometers of pipe because it was the highest pressure, being at the start of the pipeline. It was low-lying, so if there was any leakage, it would have caused a huge amount of environmental damage. And it was going through residential areas as well. It was a highly corrosive area. But what was the interesting point about this is that one of the few rectifiers that had been maintained on this line was located in this first section of the pipeline. And when we did the close interval survey, which one would have done in an indirect assessment phase of the project, we discovered that there was only about 1 kilometer of the pipeline where the wrapping was in very poor condition. And for the rest, potential was pretty good. So this was then subjected to effectively direct assessment. And it was found there was just the wrapping that had failed. And because the rectifier had been kept operational, there was no metal loss on the pipeline itself. It was found that section of pipe was in fact in good condition and was able to be used as found with just 1 kilometer of rewrapping instead of 10 to 15 kilometers of replacement.
If you think about the scenario, really was the perfect storm, and it's lovely that cathodic protection can avert these dreadful storms. It's really quite encouraging from a CP perspective. And talking about cathodic protection, sometimes CP systems don't work as we anticipate, or they appear not to be working. And the ECDA principles can also be used in a sense to help us interrogate whether cathodic protection is working. We worked on a water pipeline with that sort of scenario.
That's correct. We had a pipeline where it was a new pipeline, so there was no question as to whether the pipeline itself was functional or not. But the challenge was that the cathodic protection system had to be proven in order for the pipeline to be handed over to the client. And so we embarked on a series of measurement techniques of stray current recordings, measurement of coupon potentials, using what's known as the intensive method of IR-free evaluation, because with the stray current, unfortunately, 15 odd years ago, you weren't allowed to switch off the trains, unlike people are doing regularly now. So we couldn't get rid of the interference, and therefore you could not do a conventional off potential survey because you couldn't get an off potential. And so we used the intensive method for interpolating that. The problem with this intensive method is that it only works where there is a defect, because it is based on the lateral potential gradients in the soil. So we used a hybrid close interval survey to locate the defect, and then did the 13509 evaluation and calculated the IR free from the potentials and the gradients. And then that was then further proven by physical inspection, exactly the same as we have with the direct assessment phase of the ECDA process. To give you an idea of the work, we had test posts at regular intervals, and the test posts were fitted with coupons. The coupons were accessible for monitoring through those little manholes or inspection hatches you can see at the base of that test post. You can see there we had some pretty severe stray currents along the line, so there was no quiet period. A lot of stray current evaluation principles say, no, we'll take your measurements during the quiet period. This particular graph shows you that there just is no such thing as a quiet period. And when you evaluated or looked at the stray current profile along the line, that's the minimum, average, and maximum negative potentials. And you can see that the extent of the stray currents was quite severe on the right-hand side of the graph here, where it crossed the railway line. There's the guys doing the close interval potential survey in order to locate defects. What's interesting about this is that, as you can see, it was a typical high-felt winter, dry grass, very difficult survey conditions. But fortunately, we were able to rope in the services of a water truck in order to get
good contact
for the reference electrodes. You can imagine that water truck approach would not work if this pipeline was running through a residential area, for example. So we've got to be pragmatic in selecting the tools of inspection in the indirect assessment situation. Mm-hmm. Here we can see one of the defects that was in fact identified. What is also interesting about this graph is it goes back to what we were talking about earlier with the survey techniques. It's important to use the correct survey technique, because you can see a number of defects that are marked. 1, 2, 3, 4, 5, 7 defects marked on here, but actually there's only one that is of any significance. So the other so-called defects were indications, but not necessarily coating defects. Anyway, this particular defect was then evaluated using the lateral gradient measurement technique. And there you can see some of the values that were taken with switching the cathodic protection. You can see that there's nothing anywhere near an off potential, and the effect of the stray currents. So that in some cases the offs were sitting at -0.6, and sometimes they were sitting at -1.3, neither of which is a valid reading. And so this allows one to then extrapolate the IR-free readings from the potential of the pipe and the gradients. There you can see some of the results that were also done through one of the low-lying wet areas, where there was good contact and good correlation between the theoretical calculated values and some of the actual measured values. Going back to your comment earlier about outliers, that's a two-edged sword, because we need to be aware that every survey technique has its pros and it has its limitations as well. And so not necessarily every point is valid. And you can see here that some of the calculated, measured, the various techniques, we're looking here at the stray current averages, the coupon potentials, and the IR-free calculations. They don't necessarily always correlate. So whilst we cannot ignore the outliers, we need to take those outliers and evaluate them further to make sure that the data is valid.
I suppose it reiterates the use of multiple survey techniques to confirm the data that you're going to make extreme decisions based on.
Absolutely. And extreme decisions is a very good description. So here's a nice close-up picture of a defect, a wrapping defect that had been located. You can see the white calcareous deposits around the defect resulting from the operation of the CP system. And when that defect was opened up, there was although there was some staining on the surface and discoloration, there was no metal loss. And those photographs are of a pipe surface. It doesn't look very dramatic. But when you think that that's the sort of excavation that you have to undertake in order to do a direct assessment, you can see that it is not a trivial affair.
And we don't enter into that excavation process lightly. I think that was also something that Francis was harping on about with us over the past few sessions, was excavations are expensive. You're obviously putting your pipe at risk because you're potentially going to damage it while you open it up. So those are all things to take into consideration. That trench is enormous.
I think that was about 100 grams worth of excavation, never mind any. So the conclusion of that little exercise was that the pipeline itself was in good condition. It had no measurable metal loss. It validated the indirect assessment methodologies that had been undertaken. And at the end of the day, it really also underlined the principle that you've just mentioned, that you don't make a decision based on a single measurement technique.
Thank you, Neil. I think that's been quite helpful. It's always nice to see some of the war stories. And it reminds me a little bit of a good detective story where the final big reveal always draws on some arbitrary historical information that was mentioned in passing. And in some ways that relates to the ECDA, where the background information is so key, and sometimes it's that seemingly innocuous event in the history that can have a profound impact. And the ECDA process really helps us to put that puzzle together and come up with something meaningful.
Yes, it really emphasizes the necessity for maintaining the records. And we were involved in operating of CP systems for one of the big utilities for many, many years. And then somebody came in, reorganized the whole department, and threw away all the files.
And the tragedy of that being lost is enormous. And I think as we draw this season on ECDA to a close, I think there are really two significant aspects to take away with us. And the first is, please keep historical information as the treasure it really is. It's not just the stuff in museums that's valuable, but information about our assets is profoundly important. And the second is, and you've seen today, even in the discussions, during the indirect assessment stage, do not rely on just one single survey technique or parameter. The more varied the types of surveys, the better the chances of gathering rich and meaningful data, and those can be used, obviously, to draw relevant and valuable conclusions. So with that, we really have reached the end of this bite-sized corrosion mini-series where we've chatted quite extensively about ECDA. I'm hoping that you found it useful and valuable, and that you'll be able to implement some or all of it into your own experience.